Okay, we're on. You know, everyone's immediate. Yeah, we're on. Okay. Everyone's immediate impression is they want to know how they did right away. But you know, it's not good to have that impression because you become too attached, right? It's like someone told me when you get your reviews back on a manuscript, right? You want to submit a revision right away, but that's not a good idea. Usually it's good to wait a little while, right? So it's good to wait a week before talking about the exam, just so, you know, exams are not life and death, they're not the end of the world, right? So we let things settle and we'll talk about next week. So I always like to wait a week at least to look at the exams and go over them. So we'll go over them next Tuesday, and today we will pick up where we were before the exam. So we only have 6 weeks left of the semester. That's crazy, right? I was looking at my calendar today, and so it means it's gonna go fast, and so we got to keep moving. So I'm giving you another problem set today. Where are my notes? Where are my notes? Because, okay, here we go. So let's go right now. John, is that okay? Can you check me?
Yeah, you actually have more space.
Okay.
You're kind of a weirdo.
Is it? Can we fix it?
Exactly that. And we would, because you're blocking the dotted line. Okay. That's a good spot.
That's good?
Yeah.
Okay.
Cameraman.
Okay, great. So, you know, first announcement is to realize that there's only 6 weeks left. Okay? Only 6 weeks left in semester. And there's a lot to pack in, right? We have a final exam, you just took an exam, right? We have a Monte Carlo project and probably at least three more homework problems besides the Monte Carlo project. So it's gonna go fast, right? And so I'm giving you a problem set today. That would be problem set 5. Is assigned today. And you know, looking at the calendar, I really have to make it due in a week, just so we stay on track. So it's due next Thursday. This would be October 22nd, okay? And this problem set is on stuff we did maybe 2-3 weeks ago. It's on fluctuations mainly, grand canonical ensemble. So it's due in a week. We'll be back to normal office hours next Monday. This is, I would say, a kind of a challenging problem set. So I'm gonna say a bit challenging. So make sure you spend time on it. There's only 4 questions, but they all are different and a little tricky. 3 of the questions you can actually find answers to in the books. Okay, so you know, it's up to you, right? I would strongly encourage you not to just copy the answers from the book, right? Try to do it on your own. Use the book to check your work, and if you really, really get stuck, look at the book, but obviously you're not gonna learn anything if you just copy it straight from the book. So I realize that the solutions are in the book. That doesn't mean they're not important problems to do, so I'd like you to do them on your own, okay? So that's the caveat of the problem set. If you really wanted to, you could copy the solutions from the book and it would take you 10 minutes, but you wouldn't learn anything. So that's problem set 5, and we'll have office hours next Monday. And we are a little behind on reading because I didn't assign reading for the ideal gas stuff because of the exam. So I want you to read chapter 5. It's a really short chapter. So Macquarie chapter 5 is on monatomic ideal gases. It's short, and so that will catch us up to the reading. Okay, questions before we get started? And I promise we'll talk about exams next Tuesday, right? But we are moving on. Okay, then let's get started. How am I over here, John? Is that fine?
Solid.
Good. Okay. So, does anyone actually remember what we were doing before the exam? It was hard for me to remember, right? We were doing diatomic gases, right? John wanted to do H2, and I told him it was too hard. We had this discussion of why. My voice is kind of shot. I promise you I'm not sick. I don't know why my voice is shot. Too much, I don't know. Anyway, we're doing diatomic gases. In the Boltzmann limit. Okay, so we're doing an ideal gas of heteronuclear diatomics. And the reason we're not doing homonuclear diatomics, right, is because the rotational states are coupled with a nuclear spin because of symmetry considerations. And that just makes it slightly trickier. So we're going to ignore that complication. And so last time, right, we drew a picture. Last time, I mean before the exam, like this. And here's our favorite model of a diatomic, 2 atoms on a spring. And we can say this thing can move, it can translate. And there's some part of the Hamiltonian that governs translation. It can rotate. There's some part of the Hamiltonian that governs rotation, and it can vibrate, right? And that's our physical intuition of a diatomic. We wrote down the full Hamiltonian of a molecular system, and it looked complicated, and it also looked nothing like this picture. Remember that? And so what we said is we were going to go through transformations, okay? And so we were going to make a sequence of transformations so that our Hamiltonian looks more like this physical picture. And I think this is where we stopped. We maybe went over the first couple last time. For the Hamiltonian. Right, I'm not going to rewrite that expression. It was long, complicated, it took us a while. The first thing we said we were going to do was we're going to go to center of mass coordinates. This is pretty much always what you do to separate out translational motion. Okay, so we're going to transform to center of mass coordinates. Okay, to separate overall translational motion. Okay, and actually, I'm going to tell you which of these are exact and which are approximate. This is exact, right? This is just a coordinate transformation. We are not losing any details here. There's no approximation. Second is an approximation. The second is we're going to use the Born-Oppenheimer approximation. Okay, we're going to make the Born probably the most widely used approximation in quantum chemistry that lets us separate out electronic and nuclear motion. And this is an approximation. This is not exact. And what this approximation entails is electrons are so light compared to the nucleus that they move essentially instantaneously, right? And so that means as my nuclear move, my electrons are perfectly responding. And so what this means is we solve what's called the electronic wave function, okay? Assuming the nuclei are stationary. And this is because the nuclei move so slowly. Okay, so that's our assumption. We solve for the electronic wave function assuming nuclear stationary, and this gives us what are called Born-Oppenheimer potential energy surfaces. Okay, so this gives, so I'm running so low, gives Born-Oppenheimer, say, potential energy surface. Okay? And, that's a really important concept, but that's a discussion for quantum mechanics class. So I'd love to discuss this in more detail, but it's not the right class. We can talk about it in office hours if someone wants to talk about that in more detail. 3, we're going to assume that only the ground electronic state is thermally populated. Okay, so typically, that's almost always true. Only the ground electronic state, right? You don't have thermal excitations of electrons only when you shoot light at them. You need higher energy. Is thermally, let's just say, accessible. And in this state, we're going to assume that vibrations are harmonic. Okay? Okay? And in ground state, assume vibrations are harmonic. Okay, so this is, of course, another approximation. Why, can anyone tell me, why is it a better assumption to assume vibrations are harmonic in a ground state versus an excited electronic state? Is that intuitive? Kind of? It's intuitive, yes? Harmonic is just a Taylor expansion, right? You're thinking about a well, and the harmonic term just tells you the minimum of the well. And so if your well is really deep, then all your particles, all your vibrations C is the minimum. But if your well is really shallow, then they go far and far, and that is no longer harmonic, right? So an excited state is less bound. Your well is not as steep, it's more shallow, and so the vibrations go farther and harmonic breaks down. Does that kind of make sense? So that's the rationale. Okay, and the last one here, so we have harmonic vibrations, Born-Oppenheimer approximation. The last one is we're going to assume rotation is that of a rigid rotor. Okay, so we're going to assume rotation is that of a rigid rotor. Okay. And so these are our approximations. When we make these approximations, we get a nice simplification of our Hamiltonian. Okay. After these transformations, and you can rigorously see it in a quantum chemistry book. Okay. So see some quantum mechanics book. For doing it rigorously, we get a nice factorization. Of the Hamiltonian that looks like this. The total Hamiltonian, which we wrote down before, you have to look back in your notes, it's that complicated thing of Coulomb attraction, Coulomb repulsion, kinetic energy. Now it simplifies into 3 terms. A translational, which I'm just going to call it HT, plus a vibrational, which I'm going to call it HV, plus a rotational, HR. Okay? And so that's what these 4 transformations, approximations do, is they let us write it in this simple form, and now we can write down these individual components. So for translation, we get something that you would expect. The translational Hamiltonian HT is just kinetic energy of the diatomic. Okay, so it's just the kinetic energy operator, h bar squared over 2m times the Laplacian. That's kinetic energy, right? So this is just kinetic energy. Let me be careful with my m's. That should be a capital M. So make this a capital M. Why? Because this is a total mass. Okay, so M here equals MA plus MB, right? It's the mass of this plus the mass of this. And this Laplacian is for the center of mass coordinates. Okay, so this is for the center of mass coordinates. Let's say COM coordinates. Okay, so that's the translational, just kinetic energy. How about the vibration? No surprise, it's going to be a harmonic oscillator. That's what we said here, right? So the vibrational Hamiltonian, this guy, HV, is we have a kinetic term minus h bar squared over 2 mu. Okay, that's a mu. A kinetic term, d squared dx squared, right? Because my vibration is just one coordinate, so x is just one coordinate, the Laplacian and one coordinate. And then we have a potential term, 1/2 kx squared. Okay? And so this is really just a harmonic oscillator. With a couple special terms, mu is what's called the reduced mass. Okay, so it's mu is neither the mass of A, the mass of B, but it's reduced mass, and it's this, it's MA times MB over MA plus MB. And if you want to remember what reduced mass is, just think about units. Okay? You're going to have a product here and a sum here so that your total units give you mass. Okay, and this is called the reduced mass. And you always get a reduced mass when you transform to center of mass coordinates. Okay, so this always happens when you transform your coordinates. So that's what mu is. What is x? Anyone know what x is? X is not, it's not the position of A, right? It's not the position of B, but it's the bond length. And it's not just the bond length, it's the difference of the bond length from the equilibrium bond length, right? So x is this. X is, I'm going to say RB, the bond length, minus RB naught. That's the equilibrium bond length. Okay, so this is the bond displacement from equilibrium. Okay, so it's the difference in the bond length from the equilibrium bond distance. And so those are the definitions of the variables, but it has the form of a harmonic oscillator, so of course we're going to get the same wave function in the eigenvalues. Okay, so we know these two Hamiltonians, and our last one is rotation, right? So, and this is going to be a rigid rotor. That's what we say here. So who can tell me the Hamiltonian of a rigid rotor? HR, right? So rigid rotor, just kinetic energy. How do we think about this? Kind of like this one. This was just kinetic energy. This is translational kinetic energy. For a rigid rotor, we need rotational kinetic energy, right? And so, what is the expression for rotational kinetic energy in classical mechanics?
Is it omega?
I omega squared?
Yeah, that's right. 1/2 I omega squared. We're not going to use omega because omega is not an operator, just like we don't use velocity in quantum mechanics. So in quantum mechanics, when we do translation, we take velocity and replace it by momentum operator. And similarly, we replace omega by angular momentum operator. Right? So we could write 1/2 mv squared, or we could write p squared over 2m. And we use p squared over 2m. We could write 1/2 I omega squared, or we could write L squared over 2I, where L is the angular momentum operator. So that's right, it is 1/2 I omega squared, but we write it in operator form as L squared over 2I, okay? Where L is the angular momentum operator, and I is the moment of inertia. Okay. Inertia really is a tensor for a more general system, but for a diatomic, it's just a scalar. Okay. Let's just write down L squared. What is the angular momentum operator? I don't expect anyone to have this memorized. Let's just write down for good measure. You do this in quantum mechanics, it's minus h bar squared. Of course, we're in spherical coordinates. So we have a 1 over sine theta, d theta, sine theta, d theta, d theta. And then we have plus 1 over sine squared theta, d squared, d phi squared. Okay, so that's the angular momentum operator, the square of it. And I don't expect anyone would have that memorized. And that's our rotational Hamiltonian. Okay, and so these are all Hamiltonians you worked with before in undergrad quantum chemistry, and you've solved for the eigenvalues and the eigenfunctions. And the important point here is to say that all these Hamiltonians, the translation, the vibration, the rotation, Hamiltonians involve different coordinates. Okay? All involve different coordinates that are mostly uncoupled. Let's just say that are uncoupled to a good approximation. To a good approximation. And so we can solve them independently, right? I said they're uncoupled to a good approximation. Why do I need that to a good approximation? Can anyone see where there's coupling? First of all, how do you know there is coupling from spectroscopy?
Oh, the rotation and vibration is coupled.
Yeah, exactly. Rotation vibration is coupled, right? You see that in spectroscopy. You don't just get pure vibrational states. You don't just get pure rotation. You get row vibrational states. So why are rotation and vibration coupled? Through what term?
X and Y.
Yeah, that's right. That's right. That's right. The moment of inertia is mr squared, or sum of mr squared, for all the particles in the system. So this depends on the bond length. Okay? And so as the bond is vibrating, the moment of inertia is changing. And so that's where the coupling is. Now, for small energies, that bond isn't changing that much. And so we approximate this as being independent of this. But that's exactly right. That's where the coupling is. So So that's just good to realize. Okay, but we are going to assume they're uncoupled for now. That's a good approximation. And if that's the case, we want the complete, say, eigenvalues of a diatomic molecule. Okay, we can now write these down. If you look back in your notes, we wrote this single particle Schrodinger equation, H phi equals epsilon I phi I, right? Remember we said phi I was the wave function of the diatomic. Okay, so this is the full diatomic Schrodinger equation. Okay, but what we've just said is that H is a sum of these three independent terms, and whenever H is the sum of three independent terms, our energies are just a sum of three independent terms. And so this means that our eigenvalues EI are a sum of the translational eigenvalues plus the vibrational eigenvalues plus the rotational, right? And we'll write down what those are, but let's immediately jump to the stat mech, okay? And so then let's do the partition function of the diatomic. And you know, this is getting more and more familiar. We want to write down little q. The single particle partition function is this deceivingly simple expression, sum over I e to the minus beta ei. This is sum over states, right? The I is just a dummy index. And because these energies are independent, they have independent coordinates, to sum over states, all we do is sum over all the translational states, sum over all the vibrational states, sum over all the rotational states. And so what this really is a sum over J, a sum over K, a sum over L, e to the minus beta. We plug in E sub I, so we have E translation. Now I'm going to put a subscript on to say what translational state it is. So I'm going to write EJ trans, okay, plus EK for the vibration, plus EL for the rotation, okay? And so this is a translational eigenvalue, this is a vibrational eigenvalue, this is a rotational eigenvalue, and because these are all independent, my sum over states is really a sum over all the translational states, a sum over all the vibrational states, a sum over all the rotational states, and these sums are independent, right? And so this is like what we saw before with sums that are independent, and you know, this was the manipulation actually for problem 2 on the exam. But whenever we have independent sums, we need to get used to splitting them apart, right? And so we can split this apart and we can write the sum over J is independent, e to the beta EJ translation, okay? That's independent from the vibration, sum over K, e to the minus beta E K vibration. These are all independent, times the last one, the rotation, sum over L, e to the minus beta E L rotation. Okay, so you always split the sum when the energies are independent, right? And so really, J, K, and L are just shorthand for the different quantum numbers for translation, vibration, rotation. So let me just write that down. J, K, L are shorthand for different quantum numbers. Right, we have different quantum numbers that govern the translational eigenstates, vibrational eigenstates, etc. So let's move over here. Now I want to define these things. Well, I'm gonna have to do it over here. This looks like its own partition function, right? A partition function has this form, sum over something times the Boltzmann factor. This is sum over something times the Boltzmann factor. So I'm going to define this as little q sub t. Okay, the translational partition function. I'm going to define this as little q sub v, the vibrational partition function. I'm going to define this as little q sub r. Okay. And so when I do that, I get my total single diatomic partition function little q is qt times qv times qr. It factors. And that's what always happens when you have a sum of independent Hamiltonians. Okay, does that make sense? Questions on that? Yeah, everyone okay with that? So this is a really, really important transformation that, you've had some practice with and we're gonna have more and more practice with. And so what we do is we solve for these independently. We do the translational by itself, we do the vibrational by itself, we do the rotational. We throw the three together to get the total partition function, and that's how we do the stat math. Okay, so we solve for all of these independently. And actually, we have to do them all different with different techniques because they're all different. Questions about that? Okay, the good news is one of them's already done for us. So let's do it. So now we have to plug through all three of these, okay? But the first one's already done. So translation is the exact same as what we did for the monatomic ideal gas. So this is exactly as for the monatomic ideal gas, right? Because the Hamiltonian was exactly the same, it's just there's a different mass, right? So the result will be the same, it's just we need a different mass. Except now, mass equals capital M, which is MA plus MB. So that's the only difference here. And so we can just write it down. Anybody remember my mnemonic, or how do we remember the translational partition function for ideal gas? 2 tricks to remember it, right? It's got to be dimensionless, and it's probably got to depend on volume.
Oh, is it volume over the Boltzmann, or what is it? It's
Yeah.
the lambda cube.
Exactly, right? So that's how you remember it. One is dimensionless, it's got to be dimensionless, and it's got to depend on volume. So it's V, and you need something with units V on the bottom. The only other thing we have is units length, the de Broglie wavelength, thermal de Broglie wavelength, so we need to cube that, right? And that's how you remember it. How do you remember lambda? Well, you don't. You look it up. Or if you're really good, you do a unit analysis. If you're really good, you remember it with a unit analysis. You can remember it's Planck's constant on top, and you need something that cancels all the units to give you length, right? And so that's how you remember it. And it turns out it's 2 pi m kBT. Okay, and we went through the unit analysis last time. So that's exactly the same, no surprises there. Let's do the new stuff. The new stuff is the vibration and the rotation. Okay, so the new stuff. QV. Okay? And so, let me just repeat my Hamiltonian. We have it up there. We have HV is negative h bar squared over 2 times the reduced mass d squared dx squared plus 1/2 kx squared. Who has a favorite method of solving the harmonic oscillator Schrodinger equation? Do you prefer ladder operators? Okay, so you would solve it with ladder operators, right? And when you do that, you'd find the eigenfunctions. We don't care about the eigenfunctions, we care about the eigenvalues. And so from a quantum class, you prove that the eigenvalues are, what are they? I'm going to call them epsilon and V. V to denote is a vibrational, N is my quantum number. What are my eigenvalues for a harmonic oscillator? H bar omega times, obviously it's going to depend on N, and you need 0-point energy.
N plus 1/2.
Yeah, so H bar omega gives you the right units. It's got to depend on frequency because you have a vibration, so you know you need a frequency. H bar gives you energy units from frequency. You could just put an N there, but then you wouldn't have 0-point motion, and so you need an N plus 1/2. Okay, so that's my those are my eigenvalues. N can be, this is all positive integers, right? And what is omega? In terms of, I have two constants in my, well, I have two molecular parameters in my Hamiltonian. H bar is of course constant, mu depends on the molecule, K is basically how strong the bond is, right? So the frequency is going to depend on both how strong the bond is and the mass. Right, so somehow this has to be related to K and mu. Anyone remember the relation? So that's a good thing to memorize. It comes up a lot. Omega is root K over M. Okay, sorry I'm writing so low. This is good to memorize. Okay, that a frequency is always the square root of the force constant K over the mass. Okay, so that's, you can always write down omega in terms of what's in the two parameters in the Hamiltonian. Okay, so that's what we need from quantum chemistry. Now we're done with quantum chemistry and we can do stat mech. Let's plug this in. Oh, and there's no degeneracy. They're all singly degenerate. That's important. Singly degenerate.
You didn't do rotor.
No, right. We'll do that. Yeah, so we'll do the partition function for this, and then we'll do the rotor. So we need the partition function. We need QV, right? We need this guy. So let's write down QV. We need some. I always like to start from my general expression, where I just use a dummy I. And now at this point you should know that I doesn't mean anything. It's a dummy index. That can be kind of misleading, but you always write it down first. E to the minus beta epsilon I V. Okay, so that's what you start with, and you think of what are these states I. Well, the states are labeled by my different N. Okay. So what this is summing over states is really summing from n equals 0 to infinity. That's my vibrational quantum number. That's about infinity. and then we put the energy in the exponent. So beta times h bar omega n plus 1/2. So beta times h bar omega n plus 1/2. Okay, so everyone agree that that's what I need to, that's the sum I need for my partition function? Yeah. How am I going to do the sum? Well, the 1/2 term is constant. It doesn't depend on n, so I might as well pull that out. So why don't I pull that out? So if I pull the 1/2 out, I get a e to the minus beta h bar omega over 2. Okay? And that's pulling the 1/2 out. And I still have to do the sum, n equals 0 to infinity. And I'm going to write it like this. I'm going to put a parentheses here. I'm going to e to the minus beta h bar omega, this whole thing to the n. Okay, so the first step is everyone agree that this is the same as this? Yeah? Okay, and I'm giving you a hint by writing this. I'm giving you a hint. So now, can we do that sum? Anyone know how to do that sum? We can do that sum. So there's a few sums that have really nice algebraic closed form expressions. Can we say anything about the sign and the magnitude of the term in the parentheses? What about the sign? It's positive. What can we say about the magnitude?
Is it geometric series?
Yeah, that's right. John got it. It's a geometric series. So let's keep going with our rationale. What can we say about the magnitude? Can it be, well, it's positive, so it's got to be greater than 0. Can it be greater than 1? No, it can't be greater than 1, right? Because, if this thing's infinity, it goes to 0. If this thing's 0, it goes to 1. So it's bounded by 0 and 1, right? So this term in here is positive less than 1. Okay, and so that's why we can kind of guess that's a geometric series, because this looks like a sum of n equals 0 to infinity x to the n. Okay, and that's a geometric series. Okay, so geometric series, so note geometric series. We have this relation. We have for if x is between 0 and 1, we have this result. We have geometric series is if we have sum of n equals 0 to infinity x to the n. This equals, well, we just write it out. It's 1 plus x squared plus dot dot dot. And this is a geometric series, and it's closed form, and equals 1 over 1 minus x. Okay? So that's a really nice closed form sum, one of the few that we can actually do. But the universe has been kind to us, right? And has given us the vibrational partition function in terms of a geometric series. And so if we plug this in, we can immediately write down a closed form partition function. Here, my x is just this thing in parentheses, and it's going to go in the denominator. This is going to go in the numerator, right? So it's this guy in the numerator, beta h bar omega over 2, and then times 1 over 1 minus x, so over 1 minus this thing. Over 1 minus e to the minus beta h bar omega. Okay? So that's a very nice closed form expression for the vibrational partition function. And note, this is exact. Okay? Well, it's exact assuming the harmonic oscillator is exact, right? That's important because it's actually the only term of these three that we're doing exactly. Okay? Anyone remember what we did for QT? We had a discussion how that wasn't exact. Anyone remember that? So exact in this case means it's true in the quantum mechanical limit. Right? So approximate means it's only true classically. Okay? And so this is true, this satisfies quantum mechanics. What did we do for QT where we took a classical limit? Yeah, the Boltzmann limit was one thing, but this is just for a single particle. We took a sum to an integral. Remember that? We took a sum to an integral. Whenever we take a sum to an integral, we are ignoring quantization. And so we're in the classical limit. So this we did in the classical limit. This is exact. I'll give it away. QR, we're going to have to do in the classical limit too. Okay? So vibration, appreciate this result because this is the only one we can do exactly. Right? And that's why we love harmonic oscillators so much in physics, right? And, you can do a lot of things with harmonic oscillators that you wouldn't anticipate. You can do phonons with harmonic oscillators. You can treat light with harmonic oscillator Hamiltonians. Okay, so we're done with two of the three, right? We did this one, check. We did this one, check. Let's do the last one. Questions before we do rotation? Okay. So rotation. Rotation's a little tricky. This is QR. Rotation's a little tricky. Let's do it. So let's write down our Hamiltonian. HR is L squared over 2I. Okay. I'm not going to solve for the eigenvalues. The eigenfunctions here are the spherical harmonics, right? You solve that in quantum. And the eigenvalues are this. We're going to label them as similar to that notation, similar to this notation. We're going to call them epsilon J R, right? This signals rotation. This is now my quantum number, okay? Anyone remember what these are? Okay, use memorization tricks. Let's get the units right. So 2I is just a constant, so that's going to follow. So we're going to have a 2I here, right? We know this needs to be a kinetic energy. So we need something with the units of L. What has units of L? What has units of angular momentum? We said this once before. This guy, right? This has units of angular momentum, H. So we know we need an H or an H bar for the L. If you have to guess, put an H bar. Okay, so we have an H bar squared. So that you can write down just based on units. And the last thing, and the only thing you have to remember is you have a J times J plus 1. Okay, so this you just have to remember. This you could maybe write down based on units. But that looks familiar to everyone, right? Okay, that's the energy of a rigid rotor. And J is 0, 1, 2, etc. Do we have degeneracy for the rigid rotor? As chemists, you should give a big nod. Right? Because if we didn't have degeneracy, our periodic table would look very, very different. Right? The reason our periodic table looks like that is because we have degeneracy in the p orbitals, the d orbitals, right? And so the degeneracy is just the different orbitals, right? So each energy level has degeneracy of, we're going to call it omega, right? We always use omega for degeneracy. J equals 2J plus 1, right? And so J and L are essentially the same. They're both quantum numbers for angular momentum. J is just a general quantum number for angular momentum. L we use in chemistry for orbital angular momentum, but the degeneracy is the same, right? And so this says if J equals 0, I only have one s orbital. If J equals 1, I have 3 p orbitals. If J equals 2, I have 5 d orbitals. Right, so that's your degeneracy. Just think orbitals, think periodic table. That's how you remember it. Okay. And this is important because we need to include the degeneracy in the partition function. So we would get it wrong if we forget the degeneracy. So let's go through it. We need to do the same thing we did here. So we need to write down QR. Let me just write down my general expression. I like to write this down so we just hammer home the point that I is just a dummy index, right? It's your job to fill in the blank with what I actually is. So that's our general form. What we're going to do is, this is the sum over states. We've seen before, probably 3 times at least, that we can convert for the canonical partition function a sum over states to a sum over energies. Okay, so let's convert it from a sum over states to sum over energies. Okay, and this is what I told you not to do on problem 2 of the exam. Why? Because that's how you did on the homework. So that's why I told you not to do it that way. But it's a powerful thing to do, and I hope we remember how to do that by now. When we convert to a sum over energies, I'm just going to write a sum. I don't want to put an index here. What do? We go from sum over I times the Boltzmann factor to we need a degeneracy times p sub e, right? So we need the omega in here. I'm going to label it with J. Okay. My energies are labeled by J. So my sum over E, I can just write a sum over J because J indexes my energies. So I could have a sum over J here, 0 to infinity. And now I substitute in the energy for a given J. E to the minus beta times this thing, h bar squared over 2I j times j plus 1. J plus 1. Okay. Everyone okay with that? Right? Everyone see how this is a transformation from a sum over states to sum over energies, right? By putting my degeneracy. Okay, so let's now put in our degeneracy and see if we can do the sum. So let's go over here. Okay, so let's go up here and rewrite it. So we have QR equals sum over J equals 0 to infinity. Now let's put in what omega J is. It's 2J plus 1. 2J plus 1 times this thing. Now I'm going to put in what beta is. It's KBT. So I'm going to write e to the minus h bar squared j plus 1 over 2I kbt. Okay, so that's the sum I have to do. We are not so lucky, okay? This is not a geometric series. It's not any other series that has a closed form. It's impossible to do exactly. It's actually easy to do with a computer. So if you don't like the approximation I'm going to do next, just know that you could do this to arbitrary accuracy with MATLAB or Python, right? You would just plug this into MATLAB, take j up to 1,000, and you'd have a partition function to as high accuracy as you want. So we don't really need to do the closed form, but it's nice to have. So this sum is impossible, okay? Sum is impossible to do exactly. It's easy numerically, right? And especially, right, as you guys are PhD students, some of you are almost PhD students, you have to sort of transition your mindset into what we teach you in classes. Anything we do in class, we only do analytically, right? But in research, being able to do things numerically is just as powerful, maybe even more powerful. So just because we can't do this analytically, there's no reason if you had a research problem that you couldn't do this numerically, right? So that's an important thing to start thinking about. Okay, so we can't do it exactly. We're going to make an approximation. Let's define something first. I want to define a rotational temperature just to get rid of all these constants in here. So I'm going to find theta r. It's going to group all these constants so I don't have to keep carrying them around. H bar squared over 2I kb. Okay, that's just a definition. This must have units of temperature, right? Because in my exponent, I have theta over T. That has to be unitless, so it must have units of temperature. Okay. This has units of T. So let's call it a rotational temperature. We'll call it a rotational temperature. Okay. You could compute what it is for a given diatomic. All you do is you plug in I, okay, for the molecule, and you compute what it is. It's good to know order of magnitude, what it is. And so typically this thing is less than 50 Kelvin for decently heavy diatomics. Okay, so for diatomics, typically theta r, and it's units of temperature, so it's usually less than 50 Kelvin. Why do we care? Well, because we want to look at this exponential, and we want to say, is this exponential really short and steep, or is it really long and drawn out? And that's going to tell us whether we can convert the sum to an integral. Okay? So note that if temperature was much, much greater than this, right, then this exponential would be very slowly varying, right? It would decay very slowly. Okay, exponential decays slowly. Okay, everyone agree with that? Yeah, that it decays slowly as I increase j because it has a small coefficient, right? as this thing becomes infinitely greater than this goes to 0 and my exponential goes to 1. So it's just constant, right? And constant is slowly varying. Okay? If this is slowly varying, then I can replace my sum by an integral, right? Okay? So it would be a good approximation to replace sum by an integral. Okay? Because it's slowly varying. So we don't quite know how good an approximation this is until after we're done. We'll justify it later. Let's just move ahead and assume this is true. Assume we're in this limit that this is a good approximation. So I'm going to do this. I'm going to take this sum and I'm going to replace it by an integral. This is I'm kind of doing it blindly, hoping it's going to be right. Okay? And if I do this, I'm going to say QR. And the only reason I'm doing this is that I have no other choice. I can't do the sum. I'm going to say it's approximately, because now I've replaced it by an integral. And I'm going to say integral from 0 to infinity dj 2j plus 1 times what's in my exponential. E to the minus j plus 1. Now substitute in this definition to clean up my exponential. When I substitute this in, I just get theta r over t. Okay? Theta r over t. Okay. So, everyone agree that this is just a rectangle rule for the integral with a delta x equals 1? Right? Yeah? No? People look confused. How do I do an integral? An integral is just a Riemann sum in the limit as my rectangles and my Riemann sum have infinitesimal width. That's
like not by rectangle.
Okay, yeah.
Okay.
Oh, sorry. Well, rectangle rule, right? That's what you call it. You could use trapezoid rule, you could use rectangle rule. So rectangle rule is a way to do the Riemann sum. And they become equivalent as dx goes to 0 in the limit. If dx is finite, then trapezoid, rectangle have different numerical accuracy, right? So this is just a rectangle rule for this for delta x equals 1, right? Because I have integer values of j separating the terms in the sum, right? So I'm not in the limit as delta x goes to 0. And that's accurate if my integrand doesn't change over that width j equals 1, right? If my integrand doesn't change as I'm changing j between integers, then this is exact, right? And so my integrand will only not change if this is very slowly varying. Yeah? If my exponent is flat, then my integrand isn't changing during as it changed j from different integers. And that's what this says. Okay, so that's sort of the rationale here. But at the end of the day, it's only approximation, right? At the end of the day, it's approximation. It's not exact. And we will quantify how good it is. But assume we're going to go ahead with this. We can do this integral. Let's do a variable substitution. Let's let x equals j times j plus 1. Okay? In that case, dx is 2j plus 1 dj. Plus 1 dj. Okay? And let's do the variable substitution into the integral. Okay? So then q of r is integral when j equals 0, x equals 0. When j equals infinity, x equals infinity. So my bounds on my integral don't change. So I still have 0 to infinity. Okay? 2j plus 1 dj is this. All of this is just dx. So I have dx. And then my exponent e to the minus j times j plus 1 is just x. So I have e to the minus x theta r over t. Okay. So that's my variable substitution, and now this integral is easy, right? This is just equals minus t over theta r times the exponential evaluated at the boundaries. Okay, and then infinity drops out. 0 gives me 1. I have a minus sign here, a minus sign here. Those cancel, and I get t over theta r. Okay, assuming the sum to integral transformation was fine. Okay, so as long as taking my sum to an integral was a decent approximation, then I have a closed form expression for q's of r. Again, unitless, right? This is unitless. This has units of temperature, temperature over temperature. All these things are unitless. Okay, let's think about this approximation a little bit more. Okay, okay, how do you understand our approximation for, our approximation relies on this, relies on t much, much greater than theta r. And to do this, we need to note something. What is the spacing between energy levels? Where did I put it? I guess I erased it. What is the spacing between energy levels for my rigid rotor? First of all, is it constant? Careful. It's constant for vibrations. All right. A constant spacing between energy levels means you would only see one line in a spectrum. All right. So vibration, you only see one line in a spectrum unless you have anharmonicity. By rotations, you see a bunch of lines. Right. So it's not constant. It depends on J. But order of magnitude, it goes as h bar squared over 2I. Okay. So note that my spacing between rotational energy levels is, let's call it delta E. That's the spacing between energy levels, and its order h bar squared over 2I. Okay. It depends on J, but this is the order of magnitude it is. Why do I care? Because let's see what it says about this criteria. If I have T is much, much greater than theta R, okay, and theta R equals this, h bar squared over 2I KB, right? I just said that my spacing between energy levels was h bar squared over 2I. So that means I could plug in a delta E here. And so what I get, if I move the KB over here, I get KBT is much, much greater than delta E. Everyone agree with that? Yeah? This is really important because this is a very general condition that you can use in all of physical chemistry. Everyone agree with that? That argument? That I said this has to be true to go to an integral. If this is true, then this is true. This says that thermal energy, right? KBT is the amount of thermal energy I have, is much, much greater than the spacing between quantum energy levels. Tells me quantum mechanics isn't important. Okay? Because, you know, the molecules don't see the quantization if their thermal energy is so much higher than the spacing. And so this is what's called the classical limit. Okay? This, in general, is the classical limit. Okay, you can apply this to any system you want. Okay? And so, you know, we talked about a different criteria a couple weeks ago. When you know you don't need quantum mechanics, you can use classical mechanics. Here's another one. You can always use this. You just look at your spacing between energy levels. If thermal energy is much, much greater than delta E, you throw away quantum mechanics. And that's what we did here by going from a sum to an integral. And so this is actually a classical result. Okay? And so this means that QR equals T over theta R is a classical result. Okay, we started from quantum mechanics, but then we messed up quantum mechanics here. Right? So you could actually derive this with classical mechanics in its general. And so in the classical limit, quantum mechanics is not important. Or quantization is unimportant. And so that's a condition you can use anyway. Can we treat electrons with classical mechanics? I hope not, right? Why can't we treat electrons with classical mechanics? Now you can trivially answer this if you know orders of magnitude. Right? We should know these orders of magnitude. So what are these for electrons?
We say KBT is at like 2.5 kilojoules?
Yeah, so this is 2.5 kilojoules per mole. What's the spacing between electronic energy levels?
Depends on your system.
Does. True. Otherwise, the universe would be boring.
Yeah.
That's true. But order of magnitude, usually, unless you're a metal, unless you're a conductor. Suppose you're a band gap. Either you're a band gap solid or you're a bound molecule with a HOMO-LUMO gap. An electron volt is a pretty good estimate, right? So an electron volt is pretty much the energy you need to excite an electron to an excited state. You know, order of magnitude. Electron volt is 100 kilojoules per mole, right? So for an electron, this is 100 kilojoules per mole. This is 2.5. Obviously, this is not true, right? And so you can just apply this condition to any particle, any system you want, and say when quantum mechanics is important. Okay, so that's a general way of looking at this. And whenever we take a sum to an integral, that's essentially what we're doing. We're throwing out quantization. So I'm almost out of time. Let me just summarize and tell you where we're going to start off next time. We've now solved for all of these. We've used approximations for these two. We did this exactly. But as long as you're happy with my approximations, we know it's going to be true at high temperatures in the classical limit. Our summary is this. We're using Boltzmann statistics we're in the Boltzmann limit. The Boltzmann limit tells us we can write the system partition function as q to the n over n factorial. Okay. For the system, we just figured out what little q was. So we plug in for little q, and so this is qt times qv times qr to the n over n factorial. And we've just written down expressions for all of these. Okay. And what I want to do is I want to define this thing as big Q T, big Q V, big Q N. Okay. A system partition function for translation, a system partition function for vibration, system, not N, sorry. I'm thinking TV and N is TVR, right? Rotation. That's just a definition. I can always write down a definition. In order for this definition to be true, obviously I can split this into 3 factors, but my n factorial has to go somewhere. So anyone want to tell me where I should put my n factorial? Let's just write this down. We have q t to the n, qv is q v to the n, qr is qr to the n. We have to put the n factorial somewhere. Where should we put it? Yeah, let's put it in translation, right? Because translation is the only degree of freedom where the particles can be, we need to worry about the distinguishability, right? Because this is just an intramolecular property, right? So here's my definitions. And so now we're done. And so now we can do thermo. Okay, and I'm out of time, so next time we'll do the thermo. We've solved for this, and we can do thermo. We can compute the thermodynamics for these different contributions. So we are almost done with the stat mech of ideal gases. See how fast that went. It won't go as fast for other systems, I promise. Okay, great. So take a look at your homework. Like I said,